Hello everyone, welcome to the Sigma Mathematics Competition 2021 opening ceremony, and welcome, sir. Let me give a brief overview of the contest. The Sigma Math Contest is a challenging international math contest organized by the math community of our organization, that is PhiCalcX, and it has been sponsored by Wolfram, Ripple.it, and AOPS. The question level of this contest varies from AMC to AIME, and we will tell you more about this during the instructions time. That will be after the talk of by sir. And the motto of SMC is to make students enjoy the problems and not to take stress, so don't feel any tension, just relax and give the test. And now we will inaugurate this session with a talk by our guest speaker, Dr. R. Ramanujam, and he is from Institute of Mathematical Sciences, Chennai. And today he will be telling us about mathematics of voting. So let me tell a bit more about sir. So Dr. Ramanujam is a professor of Institute of Mathematical Sciences, Chennai, as I told earlier. So his research interests include mathematical logic and theory of computation and their applications to the theory of distributed systems, game theory, and security theory. In 2010, he was a Lawrence Fellow of the Royal Netherlands Academy of Sciences at the Netherlands Institute of Advanced Studies. And in 2020, he was awarded the Indira Gandhi Prize for Popularization of Science, which is a prestigious award given in India. So now we request sir to start this session with a warm welcome from the SMC team.
Thank you very much. It's a pleasure for me to be part of this wonderful initiative. It's a pleasure. Problem solving is the essence of mathematics, and the Sigma Mathematics competition is encouraging that, nurturing such a culture. It's absolutely wonderful, and thanks for inviting me. I've chosen the topic as mathematics of voting mainly because social choice, mathematics, and society, these topics don't really get looked at. So I thought it might be fun. But there is no particular syllabus for me to cover, so I'm just talking something. So please feel free to interrupt at any time, ask any questions, say it's boring, anything is okay, right? I can't see you people, so I don't know what you're thinking or what you're doing.
So actually the
So,
thing is, when I'm trying to switch on my video, I think
yeah, yeah.
Google has the law enforced that we cannot switch on the video because we are below 18. So I
Sure,
think,
no problem. I'm not even bothering about. I'm only saying that since I cannot see, I don't really know what you are. So the only way is for you to interrupt and talk. That's all I mean.
yeah,
Yeah, I
sure sir.
understand that video can be a problem, but yeah. So let me share screen and I'll start my presentation. But as I said, please do interrupt, talk, ask questions, say anything. It's absolutely fine. You're most welcome to do it. Right? Okay. So, and Prithvish, tell me, said half an hour, right?
Yes sir,
So maybe,
up to you sir, up to you sir.
that's okay. No, but maybe around after 20, nearly when it's almost half an hour, give me a warning in case I go on, so that I can curtail myself and stop. Okay.
Okay, so I will just
Okay.
write in the chat.
Yeah, or no, interrupt. It's better
Okay,
because
okay, okay, sure sir, sure
I
sir.
may not be watching the chat.
Okay,
So
sure sir.
yeah, once you start sharing screen, it's difficult to do that. That's all.
Yeah,
Yeah.
yeah.
Okay. So here is the yeah. So here is the title, mathematics of voting, right? And what has voting got to do with mathematics, right? What are elections? What do these things have? Okay. So first, let me thank uh, Prithvish and SMC for this invitation. It's a pleasure. Do feel free to interrupt. Okay. See, now we have what is it? What are you doing when you are voting? Right? You have a bunch of candidates or parties, and you have some preference among them. Right? In general, what's the rational basis to make a choice from a set of alternatives? For instance, you want to buy a mobile phone. Factors can be price, how cool it looks, what my friend thinks, whether it's heavy, all sorts of things, right? All kinds of factors. But finally, all these factors can be brought together, can be thought of as your preference relation on the phones available in the market. Now, of course, you don't have information about all the phones available, but let me assume that for the moment, that you have, all the phones that are available, and you have some preference, and you rank them in some order. Right? Now, if you prefer iPhone over Samsung and Samsung over Sony, it's reasonable to expect that you prefer iPhone over Sony. That means that it's very reasonable to say that your preference is transitive, right? It's a transitive relation, right? And usually preference is not total, right? That there are some choices that are incomparable. But to keep things simple, I'll assume that you have a total preference relation. That means you order everything. You order everything in one linear order, right? And now typically you can put numbers, right? I like, for this is our Indian, education system style. You put marks for each of these out of 100, right? That will automatically order them in a linear order. You can always do any such step, right? So the main idea is that you have some preference. So this is what making choices is about. That you have some preference and you have an ordering on the possible choices. Yeah? Now comes the question. Now, if Prithvish has some ordering like that, Anant has some another ordering, and Gauri has one more ordering. How if you have a group like that of 15 people, each having one ordering, is there a way to say that the whole group has some preference? That's basically the idea of elections and voting. If let's say you have a group of 5 friends, and let's say there are some parties, right? You can call them TMC, CPM, Congress, BJP, whatever, right? Now each has a preference over parties. Let's assume that it's a total and transitive relation, right? Everybody has a linear order, basically. Can we somehow infer what the group prefers? Suppose I give you this, if there are k candidates, there is a k vector associated with each person. Suppose I know all the k vectors. From that, is there some mathematical way to infer what the entire group prefers? This is what, ideally, this is what voting is about. If you think about it, what is an election? There are some candidates, parties, whatever you can call it. Take k of them, right? And each voter has a preference relation over all of these. Now, in our voting system, you just vote for one. But in principle, you can think of you're giving the entire preference relation, the entire ranking, right? Giving marks or whatever. Right? Now, if society knows this ranking from all the voters, from there, is there a good mathematical way to infer the entire group's preference? Any ideas? What would you suggest? Somebody would like to tell me what you would do? Suppose you have got the rankings given for all the voters. You have got it. There are only 5 now. So let's say there are 2 parties, 3 parties, right? So for each of the 5, you have got, some preference given, some vector given. How will you infer? Anybody has any idea? Yes. Okay, then I'll go on. Now, we don't know how you will do it, but at least whatever you do, there should be some conditions that should be true, right? Because what are we designing? A function that takes the k vectors. There are 5. If there are 3 parties, it's 5 of 3 vectors, right? 5 vectors of size 3. Let's say red, blue, and green, right? Now, but whatever function you design must have this property. If everyone in the group prefers red over blue, it should be obvious that the group prefers red over blue, for sure, right? But if 3 prefer green over red and 2 prefer red over green, what can you say about the group preference? Well, much a majority. After all, majority prefer green over red, so you must say that the verdict is green over red. I mean, voting is usually about one winner, but you can even, mathematically, the property that you're looking for is I have got, n rankings given, and I want out of all that somehow get one group ranking. That's the problem, right? Mathematically, it's a map from n k vectors to a single k vectors, right? Now, how are you going to do this? Is the question. The majority rule is perhaps the most prevalent in society, right? Now, you say that if the group prefers A over B, if majority in the group prefer A over B, right? That's a very simple function. Unfortunately, this is problematic. Now, if each preference relation is total, that is, you've got a ranking for each of them. Now, it's easy to see that the majority preference relation is also total. That's not a problem. What about transitivity? Unfortunately, transitivity doesn't hold. Suppose you have three persons. Preferences are ABC, BCA, and CAB, right? Now you can see that majority prefers A over B. You see that? 2 out of 3 prefer A over B, right? So, and then 2 out of 3 prefer B over C. Is that clear? 2 out of 3 prefer A over B. So because you've got ABC as well as CAB. And 2 out of 3 prefer B over C, ABC and BCA. Therefore, you will conclude, so majority prefer A over B, and majority prefer B over C, and therefore you will conclude majority prefer A over C. But that's not true. In fact, 2 out of 3 prefer C over A. So, majority rule is not transitive. So, if you want transitive preferences, which is very, very reasonable, right? If I prefer Colgate over Pepsodent and Pepsodent over Close-Up, I prefer Colgate over Close-Up. I mean, this is fundamental rationality. Now, that doesn't work for majority rule. So, in general, when you are taking individual, whatever preferences, political ideas, whatever it is, and from that you want to derive something for society, for any group at all, there is a problem. The rule that you come up with should be more careful than something simple like majority. So, what rule would you employ? Okay. So, for instance, you may say prefer A over B unless 2/3 in the group prefer B over A. That's a one ad hoc rule. Dictatorial. I mean, there are many politicians who would like that very much, right? Group preference is determined by single individual preferences. Our great dynamic leader prefers A over B, therefore everybody should prefer A over B. Choose the most common preferences in the group. This is what you would like. The real difficulty is how do you figure it out? And what you would really like is minimize dissatisfaction. Come up with a mathematical rule which minimizes the number of individuals whose preference is opposite to what you actually decide for the whole group, right? Your function will output some particular ranking, right? Now you may look at it and say, hey, in that ranking, B is preferred over C, whereas I prefer C over B. I'm unhappy, right? Now this unhappiness you would like to minimize, right? So there becomes an optimization problem of a kind, and then you can try to solve it. Am I making sense? Somebody has to respond now. Otherwise, I don't know.
Yes, sir. Yes, sir. Yes, sir.
Yeah. Yeah. If I'm making sense, please let me go on. But please stop me if I'm saying something bizarre. So these rules are all ad hoc, right? What we would like to do is to list desirable properties of inferred group preferences and look for ways of constructing them satisfying these properties. This is what mathematicians tend to do. You axiomatize. You write axioms saying these are properties I want of the choice, the function that I'm building, and then ask, does there exist a function that satisfies these axioms, or what's the class of functions that satisfy these axioms? This is how you mathematize. And here, what are all the axioms that you would like? Now, there has been extensive discussion in the literature over the last couple of 100 years. People have thought about what sort of things, how societies should determine choices of this kind, elections in particular, right? So people have suggested various things. One of the important things is from an Italian thinker. So, for instance, Pareto, and so this is called a Pareto preference, which is, it's very simple. What I just said, it's the most trivial thing you can think of. If every single person in the group prefers A over B, then so does the group. That's very reasonable, right? Transitivity, right? Finally, in whatever output you are saying, if the group prefers A over B and the group prefers B over C, the group should prefer A over C. This is just rational. Any group which prefers A over B and then B over C but doesn't prefer A over C, something is wrong with that group, right? So you want a group to decide things rationally. And then this is a slightly tricky thing, but it's called independence of irrelevant alternatives. Okay, what's the IIA? Independence of irrelevant alternatives. That is, if two profiles, the word profile is to talk about ranking, individual ranking. Every voter gives a ranking, right? So that's what is called a profile. Don't worry about the terminology. Basically, if two individuals' rankings agree on some choices, let's say A over B, then the group preferences derived from them also agree on that pair, right? If, for instance, Prithvi prefers A over B, and I also prefer A over B, right? So the point is, it should not matter to the group whether I differ with Prithvi on this or not, right? This is all. That so if whatever you derive from them, right? So basically, it's don't understand it like this. This is how people say it. The best way to understand it is that if I take n individuals, right, and I come up with a winner of the election, right? Final profile based on that. Now I add an n plus 1 profile. Now I find that the n plus 1 profile agrees on what, in particular, let's say A over B, right? With whatever is the group has given. See, on n persons, you finally declared A over B as the winner. Now I add one more person to the election and add her profile also, her ranking also. Now it so happens that she also prefers A over B, right? Now to the decision now, that final decision is A over B, it is irrelevant whether I have added her choice or not. It should not suddenly change simply because the alternative that we are talking about is irrelevant. It doesn't change the decision, right? So this is what this is about. And then non-dictatorial. This is something very natural you want, right? There should not be, after all, that's the essence of democracy. This is a minimum requirement in a democracy. There is no single individual whose preference unilaterally determines the group preference. In fact, you call a person a dictator if that person's preference determines the entire group's preference. So now 1, 2, 3, 4, there are 4 very simple axioms here. And you can ask now, okay, I put down these conditions. Show me a function that satisfies the trivial condition, the transitivity condition, and these independence, that is, irrelevant alternatives do not bother the outcome, and it's non-dictatorial. It's a very reasonable requirement. So how big is the class of functions? Are there infinitely many functions that satisfy these axioms? Are there finitely many? This is the kind of question that come up. Any guess on the answer? Somebody wants to? For instance, here, let me ask. Do you think, it's just a guesswork I'm asking. I'm not asking for an answer, obviously, right? I've just posed the problem. What's your guess? How many people would vote for there are infinitely many functions satisfying these axioms? They're very simple axioms after all.
Yeah, I vote.
For infinitely many? Very good. Let me see how many people. So let's see for infinitely many functions.
So you can just switch on your microphone and tell to sir.
Yeah.
I'm not sure.
Not sure. Very good. Any more? Mayedu also says.
Please switch on your microphone and then tell to sir, please.
Yeah. It's okay. Don't limit it. I want to see if somebody has anything more to say. Okay. The answer is very, very surprising. Okay. And this was a theorem proved by this person, Kenneth Arrow. And Kenneth Arrow got the Nobel Prize in economics for proving this theorem. And this was part of his PhD dissertation in 1951. In any group of at least three individuals, any assignment of group preference satisfying Pareto, transitivity, and IAA is necessarily dictatorial. That means what? If I want something that has all those three and non-dictatorial, the set of functions satisfying it is not infinite. It's not. It is empty. There is no function. There does not exist a function that satisfies all these four criteria. So,
So can you
isn't
please
that a
explain
separate?
how this works?
Yeah. I mean, I'm telling you, it's a theorem, right? I'm saying that there is no function. If the group contains at least three individuals, there is no function that satisfies all the four axioms. And his way of saying is that if it satisfies any of the other three, it must violate the dictatorial. Do you understand the statement? I'm not talking about a proof. The statement is clear, right?
Yes, sir.
Anybody else? Any question? Okay, I'm not going to prove this theorem as it is, but I'll show you a version that is slightly different, but a stronger version. Yeah. And this is one of the most influential theorems of mathematical economics and political science today. And it led to the development of an entire field, which this is what is called social choice theory. And all that I'm talking about today is really what is called social choice theory. And because you are talking about how societies make choices, and elections are one particular example of. And a beautiful introduction to social choice theory was provided by Amartya Sen in 1970. And Sen basically improved on Arrow's theorem. And he basically reworked it in a slightly different context. He looked at different conditions, and then he showed how general Arrow's theorem is. And here is Amartya Sen. So, and here is Amartya Sen's proof of Arrow's theorem. Okay. So, I'll just give you the outline. I must always warn you that any theorem and its proof, when somebody presents it, it always looks completely strange or it looks completely trivial. Unless you think about it and try your hand at it, it's hard to actually follow, right? So you should try it yourself. So here I'll present the ideas for you, and the idea is very simple, right? Let me call a coalition, right? There are n voters, right? A coalition is a group, a subgroup of voters, right? A group is decisive if everyone in G prefers A over B, then so does the outcome, right? So that means what? Is this clear? Clearly, the entire set of individuals n is decisive, right? If n is the set of individuals, if everybody prefers A over B by Pareto condition, the outcome also will have A over B. So, if any particular group G has this property, call the group decisive. This is just a definition. Now, Arrow's theorem then follows from the contraction lemma. What it says is that if G is decisive, where the size of G is greater than or equal to 2, right? Suppose there are n voters. Now I show that an n by 2 group is decisive, right? Then I can prove a theorem which says there exists a strict subset G prime of G that is decisive, right? You give me a set that is even n minus 1, right? N minus 1 voters who are decisive. I mean, I must make sure that it's at least greater than or equal to 2. That's all that, right? It's not a trivial set, right? So, if there is a set that you give me that is decisive, I'll show you that there is an even smaller set that is decisive. So, what will happen then? Now G prime is decisive. What will the lemma do for you? It will give you a G double prime that is decisive. You keep on doing that, and what will you get at the end? Can somebody tell me what I will get at the end? Look, there are 20, n equals 20, right? All G, no, well, you keep doing this, what are you going to get? This is G is greater than or equal to 2, right? No? Yes, Amrita? It is not an empty set. You will get a singleton set. Is it clear? If I keep on doing that, remember that the thing applies only for size of G greater than or equal to 2. So when does it stop applying? When size of G is less than 2. So that's exactly, yeah, Amrita, exactly. That's why you get dictatorial, right? I wanted something. So this is the where it's a beautiful idea, the contraction lemma. It says I look at any function that satisfies the three properties: Pareto property, independence of irrelevant alternatives, and transitivity. Then it says if there is a decisive group at all, right? Now there must be one. We already know the entire set of individuals n is decisive. So you can start with n. It'll then this lemma will give you something that is n prime. It's a group that is of size strictly smaller. Then I apply the lemma. I keep on repeatedly applying the lemma, and then I'll get a single one, and that is dictatorial. That's exactly what Arrow's theorem says. Okay. So this is, as I said, this is not Arrow's proof, but Amartya Sen's proof, and it's a beautiful proof. Okay. So the contraction lemma is the heart of the whole matter, right? If you understand the contraction lemma, you understand the theorem. Now, how do I grow? So yeah, so how do you prove the thing? Since G has at least two members, partition it into non-empty G1, G2, so that at least one of the two is decisive, which must exist, and then apply. And now you say G is almost decisive if whenever everyone in G prefers A over B, and everyone outside the group prefers B over A. So what I mean is, you're kind of looking at the maximal subset that satisfies A over B, right? It's maximal because anybody outside it has the preference the other way. Then any such maximal set will give you A over B. So clearly every group is almost decisive, and we show that the converse is true as well. And that's enough to prove the contraction lemma. So to prove the contraction lemma, what do? I'm starting with something that has at least two members, so I partition it into G1, G2, right? And at least one of them should be almost decisive. What is almost decisive? It means that it's a maximal one, such that if that maximal set, it has the property that if that group prefers A over B, the whole group prefers A over B, and it's the maximal such set, right? And so how do I do that? First, I have to partition G into two such sets, such that one of them is almost decisive. Well, pick some choices. I mean, let's do this all with ABC, right? I mean, this whole thing works for whatever number of voters, right? Finite number of choices. So, and some ranking profile over G1. Let's say we have vector CAB, right? So A is preferred over B, and G2, it is ABC, and outside any G, you have some BCA, right? So G1 has A over B, G2 has A over B, but outside G, it is C over, B over A. Now, if G1 is almost decisive, we are done, right? Suppose G1 is not almost decisive, by independence of irrelevant alternatives, right? We can argue that the outcome prefers B over C, yeah? And because, right? That's the point about independence of irrelevant. Similarly, if, remember, G1 has the vector CAB and G2 has the vector ABC, right? IIA is independence of irrelevant alternatives, right? Basically, it says that for that group, for a particular group, if you have decided A over B, adding some more people is not going to change, right? Adding some more people who also prefer A over B is not going to change anything, right? Remember that G1 has CAB, so it's A over B. G2 has also A over B. So as far as A over B is concerned, it doesn't make any difference. Similarly, as far as G2 is concerned, right? G2 is not almost decisive. Again, by this, we can assume that outcome prefers C over A, right? Because that is what you get from G1, yeah? Because you're getting it from the opposite side. So by transitivity, we get that the outcome, so we know that the outcome prefers B over C, and the outcome prefers C over A, therefore the outcome prefers B over A. But we have said that you gave me a G that was a decisive set, right? And everyone in G prefers A over B, so the outcome prefers A over B as well, and that's a contradiction, because you just proved that it prefers B over A, and I've got A over B, right? Remember, G1, G2 is a partition of G. So all of G prefers A over B, right? Remember, it's CAB here and ABC here. So it's always A over B. But that's where I get the contradiction. So this is the contraction lemma. Now, I've basically said from a decisive set, I can get an almost decisive set. Well, but that's not good enough because I have to go from a decisive set to a smaller decisive set. How do I do that? And that's called the field expansion lemma. And that says if you have any almost decisive group, actually it is decisive. How do you do? We need to show you take any ranking Ri and some choices x and y. If everyone in G prefers x over y, so does the outcome. That's when it is decisive. Now again, by independence of irrelevant alternatives, it suffices to show that for a pair AB, and if I take some other profile ranking Ri prime, which agrees with Ri on AB, that's all that I need to look at because I'm only looking at outcome of A over B. Now take some third alternative C, right? Now what do? I define this, I have to define this R prime, right? I say basically over A and B, I do whatever Ri does. But for outside G, right, I use, basically I put, I do the same as R over AB, right? And over G, I use some ACB x for other x, right? And outside G, I use C over A over X and C over B over X for the other X. Don't worry about this particular construction. As I said, you have to sit and try out different combinations and you will get it over this. Okay. So basically, it's some slight combinatorics that you have to set and work on. Yeah. So basically, that's the field expansion lemma, and put it together with the contraction lemma, you get the Arrow's theorem. So basically, elections are also about aggregating social preferences from individual preferences. And people have been talking about this for a long time. 18th century Condorcet and Borda. In 19th century Charles Dodgson. By the way, is that name familiar to anybody? 20th century important names, Kenneth Arrow, I've already mentioned Amartya Sen, Sattrat White, all these people. By the way, who's Charles Dodgson? Does anyone know the name? Anyone out here know the name?
No, sir.
No? Okay. Fine. You may know of this person as Lewis Carroll, author of Alice in Wonderland. So he's a mathematician, clergyman, and wrote beautiful books. Alice in Wonderland is a wonderful puzzle book, and Lewis Carroll is a pen name. Okay. So here is Marquis de Condorcet, and this is Jean-Charles de Borda. So they all, there are very famous rules that people came up with. Now, the one that we use in India in our general elections is first past the post, right? What is that? You simply sit and count. Everybody puts one vote. I mean, basically votes for one candidate, and whoever gets the maximum number of votes wins. This is called plurality. Each voter awards 1 point to her top alternative, and the one with the most points wins. And this is the one used in almost all political elections. And then there is Borda count. So there is the Borda that I was mentioning. If you have M alternatives, let's say 3 parties, each voter awards M minus K points to his kth ranked alternative, right? So, and if you think about it, it makes sense, right? 1, then 3 minus 2, 3 minus 3, and so on, right? So it's basically, you call it 0, 1, 2, the ranking. So the one with the most points wins. And this is in fact used for the national elections of Slovenia. Then there is veto. For each alternative, count last place for each alternative, count the last place votes, and the one with the least of them win. Basically, this says, and is also used in some countries. So everybody says, I hate this fellow, right? I don't care who wins, but I don't want BJP to win. Let's say, suppose I say, right? So you look at the last place votes for everybody and say, okay, how many last place votes does BJP have? How many last place votes Congress has? How many last place votes Trinamool has? And so on. Republicans have, Democrats have, whatever. And then you say that the one with the least number of last place votes, right? This is the one that hated by very few people wins. And this is also used in some places. And then you have multi-round votes, which are single transferable votes. I mean, this is kind of thing used in Ireland, Malta, Australia, and New Zealand. Basically, you keep doing this, conduct elections like what we do, but whoever has the least number of votes, anything below the point is eliminated. You have next round, and among them you conduct this. Anyone with the least is eliminated, and so on until somebody is eliminated. And then there is plurality with the runoff, and this is the French elections. Basically, first round you have everybody, and the second round winner of a pairwise election between these two.
So can you please explain the single transferable vote once more?
Okay, there are M-1 rounds, right? So there are M candidates, right? What I do is in each round I take the last person, throw the person away, but whatever are those votes are actually so you see that, right? And the survivor to the last becomes the winner, right? So every round somebody is eliminated. For the remaining person you have election again.
Okay, so at the last only one person remains there. So who
Correct.
is the winner?
So he's the winner. Yeah. Now Condorcet winner is more fun. Conduct pairwise elections. What does it mean? I look at you look at the ranking. Look at if A were to contest against B, who will win, right? Then you look at A were to contest against C, who will win? A against D, who will win? Like that. Look at it pairwise, and from there is a rule that says, okay, who will win, who will beat every other alternative to a pairwise election. But this is one where a winner may not exist in general. So that's where. Okay, so let me not go over these things. So this is all to tell you that Dodson, who's Lewis Carroll, defined distance function. So now there are European Union uses some fairly complicated rules like this for deciding on a particular issue that involves the European Union, where many member countries are there, for instance, right? So almost all these rules are used somewhere or the other, and some of these rules are complex. Winners are hard to compute. For instance, we can show that Borda plurality or Borda count can be computed in polynomial time. Computing the Dodson winner is NP complete. Don't worry about it. This is to say computationally these problems are hard. Why am I saying that? Well, and lots of restrictions and preference profiles are being studied. There's a whole mathematical theory here. I just want to mention that it's a rich theory. Now, there's one issue of interest, that is manipulability. We say that a rule is manipulable, right? If there exists a profile where a voter I can switch her preference from Ri to Ri prime such that her most preferred candidate wins. So basically, what is this idea of manipulation? Some people decide that, not my actual preference. Instead, I will switch my vote from this candidate to that candidate. By a few people doing that, let's say some X wins. That's called. Now there is a theorem due to Gibbert and Sadat-White, which says that any non-dictatorial voting rule is actually manipulable. That means what? If you want both non-manipulability and non-dictatoriality, again such a function does not exist. And again, this is a more complicated theorem. So basically it says that if you want your election to be non-dictatorial, it's always manipulable. But then we can show that it's true that such a function exists, you can manipulate, but coming up with the manipulation is really hard, computationally hard. So now you can use the fact that it's hard to actually come up with practical election policies, right? So with the advent of internet and algorithms that make decisions, so it's a very rich field. It's an area of intellectual endeavor that intersects philosophy, politics, economics, uses tools from mathematics and computer science. And these are very important things because remember, societies cannot be rigid about voting rules. That's the essence of democracy. Social preferences are hard to derive, and the logical difficulties in doing so need to be acknowledged and addressed. I am basically a logician, and I have looked at many of these things as from the viewpoint of logical theories. With the advent of the internet and algorithms, where you want to make all these electronic voting, etc., for making decisions, these considerations apply to a far wider variety of contexts than before. Right now, you have algorithms among which you run elections to decide on some particular thing. Right. So these are all mathematical objects, and they affect society. So it's very, very important to come understand the mathematics of these things. So it's a rich field, evolving field, lots of open problems. Uh, so I just wanted to invite you for working in a beautiful area like this. Thank you.
Okay.
Sorry I took longer, but I
Thank
hope.
you, sir, for your excellent lecture.
Thank you very much. Anybody has any particular question? I would.
Yes, actually, I wanted to ask that which voting result gives the better, like multi-round rules or single round? Which one gives the better results?
Well, here we don't have anything like what is better and worse. Uh, any rule that satisfies all your axioms is acceptable, right?
Yeah.
So the problem is that multi-round, in general, of course, multi-round rules have more desirable properties than single-round elections, of course. But instead, what you can do is to put a metric and look for minimizing in a metric and so on, and actually come up with a very complicated rule, which will, in a single round, will, satisfy all the properties. If you are willing to settle for some, remember that the negative theorem holds, right? Impossibility theorem is there, so you know that there isn't any. You have to give up on something, and so what people would suggest is make this probabilistic, allow for some randomness, allow for this, a lot of ways around it. But basically the idea is that if you want something that's practical, you want something that's efficiently computable, and something that people agree on, and something that's simple. That's very hard to define mathematically. Remember that in a democracy, if the rule is more and more complicated, it will be harder and harder to convince your population that this is how we should do things, right?
Yes.
So that's difficult to mathematize.
Yeah. So anybody has some questions? Yeah.
Yeah, what exactly is it a vector? Oh yeah, okay. I said it's a vector because it's an ordering, right? It's an ordered list.
So it's a vector.
Yeah, so it's a vector, right? So I mean, formally, I can make it an element in a vector space, define metrics, talk about distances between preferences, and so on. So that's why I use it.
So the vector
I
is
didn't
like
get into
in the vector space, we are just defining the k vector.
Yeah. I mean, every person's ordering, right?
Yeah,
When I
exactly.
say I prefer, for me, TMC is on top, then CPM, then Congress, then BJP. I'm giving you an ordered list, right? So
It's like thinking
there are
of a
k
column
choices.
vector with TMC
Yeah,
at
it's
the
a
top
point
and
in a
preference.
k-dimensional space. It's
Yeah.
a point in a k-dimensional space, right?
Yes.
Now, I have only talked about a discrete space,
Yes.
right? The moment you start putting probabilities and so on, of course, you get into real valued spaces. So, but mathematics remains uniform in all.
Yeah. So G spans the vector space.
Yeah, that's right. Yeah.
So anyone else has any questions to sir? We are now in the question answer session, so you can ask.
I can give my email address on chat so that anybody who wants to contact me for these or more is most welcome. Yeah, I put my email address on chat. What did you say was G? G is any subset of the set of voters, right? So I assumed N was the set of voters. By the way, I mean, all the stuff is interesting and practical when these are finite sets.
Yes,
But
yes.
no reason for it. Mathematically, for a problem like this, we just ask, given n k vectors, I want to come up with a single k vector that satisfies certain property. So
Yes.
it's simply a map from uh, yeah, these. And so in principle, there's no reason why the number of voters can't be infinite for this. It's like that. So we can do a lot.
Yeah.
Not that it has any particular meaning to a social election, but it's
So
possible.
theoretically, can we think of infinitely many voters?
Of course,
I think
why
we
not?
can. Yeah.
What is stopping you from doing that? You can have
Eh,
continuum many voters.
yeah.
You can have
So
all that.
then, if we just think that the algorithm would just never end, it will just continue to do that. Yeah.
Not necessarily. There are finite presentations for these things, and you can compute based on that. So,
Okay. So
not
finitely we can do that.
in principle,
Yeah.
but
Okay.
in practice you cannot. I mean, these impossibility theorems hold all the way. So,
Yes. Yes.
okay then, if there are
Any questions from others? You can write in the chat or switch on your microphone and then ask sir.
okay, thank you.
Yes, it was really interesting because I didn't know. I also didn't know about it.
Okay then,
Especially the
thank you all.
people who worked on this, the scientists who work on it.
Yeah, definitely. Yeah, I have given my email address, and I think that is the simplest way to contact me.
Yeah. So sir has given his email address. I'm just
On
posting it
chat.
again.
Yeah.
So I've again posted the email address. So if you have any further questions, you can email sir. About it.
Yeah. I mean, I welcome comments and questions and anything. Yeah. Do feel free to write. Okay then. I think we are okay. So I
Yes.
thank you all for your attention and interest.
Yeah, thank you, sir. It's a privilege to for us to. So you came and gave a talk in our sessions.
Most welcome. Happy Independence Day. It's
Yeah.
a
Happy Independence Day.
yeah, it's a great opportunity. Yeah. Okay then. Thank you all.
Okay.
Shall I say bye, Prithvish?
Uh, yes, I think it's almost over because.
Yeah.
Yeah.
I mean, unless you have anything else,
No, thank you.
I'll say bye to all.
And thank you, sir, once again from the SMC team as well.
Yeah. All the best with SMC.